Fourier series, the great discovery by the genius Euler. Any periodic function is expressed by this f t plus c. C is any arbitrary point to start function. Okay, so plus t 2 pi, we fix the period 2 pi first, and later we can expand and generalize it later. So any wave function, it repeats itself over the time. That kind of function can be expanded into infinite series using cos and sine function. Okay, how do we do that? Well, simply we assume we can do this. This is a Fourier series formula. Okay, now the task here is to find out this coefficient. So when you take an integral on the both side from c to c plus 2 pi, then simply cos and sine become 0. So we can get the coefficient a0 as 1 over pi and the integral of ft. Now, how about an? An is same way. You multiply cos nt to fx on the both side. The cos nt become cos square nt and cos sine nt. Cos sine nt just simply disappear. Okay, and this a0 disappear, so only an remains as an integral of ft cos nt. So we get an. How about coefficient bn? Coefficient bn, same thing. If you multiply sine nt on the both side and take an integral, then all the remaining terms disappear as 0, and only this term left. That's gonna be the coefficient bn. Okay, so here those are mixed term is all disappear. So c can be any value from 0 to minus pi. Can be 0 or minus pi. That means you can make a repeated function like that. That's a c equals 0. Or you can make minus pi like that. Okay, and when ft is odd function, then this is gonna be odd function and this is gonna be an even function. So wait a minute, if this is odd function, this is gonna be cos is odd function, and this is gonna be the even function. If ft is even function, then cos will be even function and this is going to be odd function. So the odd and the function odd or even is going to be preserved by this term. The change of interval c to t, we generalize to 2t, not the pi. Easily we can do it introducing new time scale. The time scale is multiplied by pi over t. So we can generalize a Fourier series for any period, and this is the odd function, and this is even function. Okay, so these repeated function, like typically electronic waveform, can be infinite series. And what's significant about this is infinite series is a discrete quantity at n, the frequency. So each frequency you have discrete quantity. Say you have time domain, some kind of repeated function. So frequency domain, you have discrete quantity like that, and that is so-called frequency spectrum. Okay, so you can look at the function by either time domain or frequency domain. The frequency domain, there are many important aspects of it. The same ft can be looked at in both ways. That's the Fourier series, important part of the Fourier series. What application we have? For example, filter. Apply filter function to the frequency domain and obtain the signal waveform. So what happens if you have a filter like a Dolby, Dolby filter? The high frequency hiss noise is eliminated, so this side is eliminated. So what's happened to the original waveform? So after you remove some of upper term and convert Fourier series into the original ft, then you will get exact waveform after you feed the signal to the Dolby filter. Okay, so in electrical engineering, the filtering is often used. This is a vital mathematics tool to analyze what's happened to the waveform. Image compression, your favorite JPEG, use this. How does it work? You have a image, you do Fourier transform in the two-dimensional, so you get the discrete value in two-dimensional table. You remember this table. If you need image, you convert it back to the original image, then you get the original image back. So amount of information you need to save is much less amount of information to save for the entire image. And that's the way it's compressed. Image file is compressed into smaller file in a JPEG. Okay, so but you cannot save infinite amount of discrete value. You have to chop off somewhere. So when you recover the image, you lose some accuracy slightly. Okay, so it's called a lossy compression. It's not 100% recoverable. You lose some. Okay. Another one is Shor's algorithm. This is the latest topics, quantum Fourier series. This algorithm used for quantum computer to break the encryption code. Okay, these details is getting to a little bit difficult, so just let you know that Fourier series is used in such an area too. Fourier analysis. What's a Fourier analysis? Fourier analysis is you get the data point actually at a different frequency, so you get the discrete data, and after measurement you convert it back to waveform. Okay, so instead of the analyzing a system what kind of waveform it has, what you do is just make a measurement at the frequency domain and recover the waveform. Okay, that's the Fourier harmonic analysis. Okay, and finally, solving some partial differential equation like heat problem in engineering, Fourier analysis is very important. So that's what a Fourier series is about. Okay, so if you are in science or engineering major, for sure you encounter this and you utilize this tool, math tools. Thank you for listening. We have other interesting subject. Please check it out, and if you like, please subscribe. Thank you.